Bismillahirrahmanirrahim. Dear students, this is lecture number 5, and today we will be covering equivalent resistance for series resistances and parallel resistances, and then we will be doing these practice problems 2.9 and 2.10, and I will also be explaining a bit about 2.11, but you will attempt it yourself. For your queries about the contents that are being discussed in video lectures, you can just contact me on my email address. I'll be just making another video for answering your queries. So do send me your problems, and I will also be uploading a lecture assignment of chapter number 1 and chapter 2 that you will be doing in a copy, and then we'll take snapshots, and then we'll make a word file and then upload it on LMS. So for assessment, that will have a weightage of 5 marks, so that way we will just be keeping the assessment also in line with the course. So that is also a requirement. We will be seeing how we can just do a quiz later on, but so far assignment is enough. But do submit the assignments and do the practice. It's very must. So starting from our lecture, what we will be doing is we will be doing this series resistance. Let me check. Am I recording or not? Yes, I am recording. This is the second time that I am just having a problem, and I just recording again this video. So my all effort of last 20 minutes has been wasted because of this video problem. Okay, so okay, Allah help us all. So today is the lecture series resistance and voltage division. I will not be doing this voltage division in this current lecture. I will just only be doing series resistance and then parallel resistance 2.5, and I guess the next topic is 2.6 for the parallel resistance. So what is series resistance? If two resistances are connected in this format, this is called series resistance, that one terminal is common. Be very attentive that a series resistance combination is only the resistances where there is no third point coming out of this point. If there is anything something coming out of this point, the third tap, then this will not be a series connection. Series connection requirement is that you must have and you only have 2 points connected at one point. So there are two resistances, one terminal of the R2 and one terminal of R2 is being connected on a single point. That's what makes a series connection. Okay, so the final result of getting a R equivalent is this one. R equivalent is equal to R1 plus R2, and whatever number of resistance you have in series, you can just add them together, R1 plus R2 and R3 and R4 and R4. So how do we reach this final result? There are few simple steps that we can follow to reach this final result. So we are assuming that current of I is passing through R1 and R2. So by Ohm's law, the voltage drop across this R1 is going to be V1, and by Ohm's law, voltage drop across V2 is going to R2 is going to be V2. So V1 and V2, if we just apply KVL here around this loop, V is equal to V1 plus V2. That's it. This is V is equal to V1 plus V2. But we already have seen that V1 is equal to IR1 and V2 is equal to IR2. That's how we reach this, and I becomes V divided by this thing, this R1 plus R2. So that's how we just see that this resistance is equal to R equivalent, because we are getting this I by just combining the R1 and plus R2 and the ohms by the form of the Ohm's law. This is very apparent that this needs to be R1 plus R2 to make the Ohm's law hold true. So this is R equivalent. Right, so this is the general form of the series resistance. This is the voltage divider that we will be doing in later chapter. And now I will be doing this parallel resistance and current division. Current division is something which we will be covering in later lecture. That is lecture number 6. I will be doing it for voltage divider and current divider. For current lecture, I am just focusing on series and parallel combinations. This is a parallel connection, very obvious. these two resistors are connected in parallel. Their both terminals need to be common. This top terminal of R1 is common with the top terminal of R2, and the bottom terminal of R1 is common with the bottom terminal of R2. That's why this is a parallel connection. So what is the end result? The end result is this one. The R equivalent is given by 1 upon R1 plus 1 upon R2, and this by simple few algebraic manipulations we can just see that this R equivalent is equal to R1 and R2 upon R1 plus R2. So this is the formula which we will mostly be using for finding out the equivalent resistance for parallel combination. Even if we have three resistances in parallel, we will still be using the same formula of two resistance. How? We will just solve two resistance first, and then we will just combine them with the third resistance, so that we don't need to apply this tedious formula. This is a very tedious, means there are a number of steps involved for finally getting this R equivalent, and this is much simpler. Right, so having said this, the final result, I will just like to go through the few simple steps by which we have reached this final result of R equivalent. So what do? We know that this V is a common same for R1 and R2 across R1 and R2, because the terminals are common with this V, so V is going to be common. But V is equal to I1 R1. If we just multiply I1 into R1, this is V, and if we just multiply I2 R2, that is also V. So this V is equal to I1 R1 is equal to I2 R2. So that's how we get I1 is equal to V1 upon R1 and I2 is equal to V. We get I1 is equal to V upon R1 and I2 V upon R2. Applying the KCL is the sum of the currents at any node are equal to 0. So that's why this is the current which is coming towards the node, and these are the currents which are going away from the node. So these need to be equal. So this is KCL, and from this KCL we know that what is the value of I1? I1 is V1 over R1 and I2 V1 over R2, and we just take the V common and we reach this V upon R equivalent. That's how we reach this final formula of 1 upon R equivalent is equal to 1 upon R2. 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. Right. So now we just do a bit of, and I just explained one more thing, that is the conductances. 1 upon R1 is called conductance. So for a parallel formula, if the resistances are available in the form of conductances, conductance is measured in moles or Siemens. So this we will be finding the combined conductances by just adding the conductances together. So this is kind of formula which was used for series resistances, but now for conductances this is applied on a parallel combination. The same is true with the series conductance is connected, so that will be equal to 1 upon G1 plus 1 upon G2. The kind of formula that was in parallel in resistance, in terms of resistance, is same form which is for series for the conductances. Right, so I hope this you have understood it. This is about the current division that I will be doing in next lecture. So what does it mean that if I is coming, then how it is going to be distributed in two branches? That is called current divider. So voltage divider VDR and current divider CDR we will be doing in next chapter. Right, so here a bit of practice for you. This is example 2.9. You will do it yourself. I will be just going through this practice problem 2.9. Here 2.9. This is the practice problem. I have just drawn the original circuit here. They would just want us to find the R equivalent resistance on these 2 points. So this is not very difficult. These all three resistances are very obviously series, because that thing is coming out of here, nothing is coming out of here, but here these two, the combined combination of 4 plus 5 plus 6 is being connected on this point. So these three resistances are replaced with one single resistance that is equal to 12. 4 plus 5 plus 3. Now this 12 volt 12 ohm resistance is in parallel because both terminals top and bottom are common, so we solve them together. 4 in parallel with 12. This is how you show parallel resistances. These are the calculations for finding out the parallel combination of two resistance. 4 multiplied by 12 and divided by 4 plus 12, that becomes 3. Now this is very obvious that this 3 ohm resistance here, this resistance is in series with 3 ohms resistance, so this becomes 6. Now 6 in parallel with 6, that is equal to 3, and then 4 plus 3 plus 3 is equal to 10 ohms. This is the answer. I go here for 2.10 practice problem 2.10. You can have a look from your book, practice problem 2.10. Here it is. They just want us to find RAB, these two resistances, points A and B. So this is the solution here. These two resistances 20 and 5 ohms are in parallel, that's why I have just replaced it with 4 ohms resistance. The calculations are here. This is in series with 1 ohm resistance, that's why this becomes 5. 4 plus 5 in parallel with this 20 ohm resistance, diagonal resistance. So 20 in parallel with 5 is equal to 4. The same calculations apply, and then this 4 and 2 becomes 6, this 2 and this 4 becomes 6. 6 in parallel with 6 is 3, this is 3. 6 in parallel with 6 is 3. Adding with this series resistance 16, so this becomes 19. So this was a small short lecture. I hope you understand it. Bye for now, and in next chapter, next lecture number 6, I will be doing current dividing and voltage dividing. Fi amanillah.